So last time what we did was look at the Rademacher complexity of this linear function class. And the point was that if the x's are, let's say, in a high dimensional space or an infinite dimensional space, so Hilbert space is like an infinite dimensional Euclidean space. If the norm is bounded, the norm of the examples are bounded, then the Rademacher complexity of the class is goes down like 1 over root n times this bound on the norm, rather than in terms of the dimension. So that was something quite interesting, and then we were going to use that to give bounds for hard-margin SVM. And then there was this contraction lemma that says that if I have a subset of, let's say, Rn, T, and then I apply Lipschitz functions, like scalar Lipschitz functions to every coordinate, let's say there are 1 Lipschitz, then the Rademacher complexity of the resulting set is at most the same, let's say, upper bounded by the Rademacher complexity of the original set. So if they're not 1 Lipschitz, they're L Lipschitz, then it's easy to just see what happens. So you just pay a factor of L in front. So let's just remind you of these things, so that I'm reminding you of these things so that we can use them today. Then we moved on to look at specific classification problems. So we have, for a classification problem, we have a response which is binary, and here we're going to model it as ±1, and then a subset X, or an X which is a subset of, let's say, RD, although later this could be any Euclidean space, even infinite dimensional. And then we look at the loss function. The basic one is the 0-1 loss. So if you have a function h that's predicting y, so you have h of x approximately y, then the your loss, the 0-1 loss, would be the expectation of this indicator that hx is not equal to y. And this just is equivalent to the probability that hx is not equal to y under the generic example from the distribution, right? X and y drawn from P. So we're going to look at the linear classifiers. We can say affine classifiers where the h is an affine function of x specified by this weight, and the intercept, or they call it bias, let's say, in machine learning. And then we have this idea of linear separation. So the distribution that the data is generated from is linearly separated or separable if there exists a hyperplane. In other words, there exists one of these h's such that the probability that y is equal to hx is equal to 1. In other words, the 0-1 loss is 0 for that hyperplane. And another way of writing it is just that the sign, because you can imagine that, oh, I think I'm missing again. Should have corrected this. This should be the sign. So the sign, the classifier is a sign of this. So you get that things are linearly separable if the sign of y and the sign of this affine function are the same. So this should hold almost surely. And then we assume that b is often 0 by absorbing this 1 here. So you can think of it as a feature of constant 1. If you augment x with this feature of 1, then you can just augment w with b, and then that would be your new w. Okay, questions? So for separable data, there is this notion of margin, which is how far, like the closest of each class is to a separating hyperplane. So there are multiple separating hyperplanes usually, and the point here is the data has a margin if something like this holds. So if I have, if I look at the distance of a generic example from my hyperplane of interest, which the distance would be as we have here, then also without loss of generality, we're going to assume that this is equal to 1. Then if we require that all the points are at distance gamma to this separating hyperplane, that would be equivalent to this, as we discussed. And so we have this definition that the distribution is gamma rho has a separable with gamma rho margin if there exists a W star in ST minus 1. This is again the set of all W such that this is equal to 1. And so W star in this means that this is the sphere in RD, unit L2 sphere. And then there's a W star and B star such that XY is in, if X and Y is drawn from P, then you have this margin separation, and we also assume that the norm of X is bounded by rho. So part of the reasoning for this is that the margin is otherwise not well defined, because if I don't let X2 be bounded or somehow the norm controlled, then I can always, so I can always multiply X here by something, and then adjust B as well, so that I can like increase gamma as I wish. So with this, hopefully, things become more identifiable, let's say. So then you can have the margin, the same definition for the empirical measure. If you apply to the empirical measure, if things are separable, then you definitely have a margin, because just the nature of a finite set of points is that like there is a minimum distance to the separating hyperplane. But the interesting thing is like this population version where basically you have infinite sample size, but things are still separated from the hyperplane. Okay, so any question? This was just a recap of some of the things that we discussed last time, right? So if you have a margin or a separable data set with a given margin, the natural thing is to try to find a hyperplane that maximizes the margin. So we have seen that the margin has this expression. Basically, the margin has this expression. So this is the distance of a point. So I have a training set, a data set of size n. And so the distance of the ith example from the hyperplane is this on either side. So you recall that yi times this is going to be positive. So this is similar to the absolute value, basically. So this quantity is the same as absolute value of W transpose xi plus b. So the minimum over I is the margin. So this is the margin for this data set. And if you maximize over the hyperplanes, which is maximizing over these two parameters, then we have the max margin classifier, right? And then we wrote this as, so the minimum, you can see that it's equivalent, that problem to introducing the slack variable. So if I maximize over alpha first, I hit this boundary, which is the minimum. And then I'm maximizing that minimum over W. And then some thought gives you that things are a scaling variance, and you can just equivalently assume that alpha is equal to 1. And so instead of maximizing 1 over norm W, we can just minimize norm W subject to this, and this is the hard margin or hard SVM. For simplicity, we often again assume B is 0. And so we're going to look at this simple form of the hard-margin SVM. So this is a convex problem, so minimizing a convex function subject to a set of linear constraints which are, or affine constraints which are definitely convex. So this is quite easy to solve. And the question is that, let's say, can we state something about the performance? And here is the result that we wanted to prove last time. So let be PV gamma rho separable on RD times plus one, like plus minus one space. Let H hat n be W hat n X. Then the hard-margin SVM. So let's say W hat n is the solution of 2, right? So this guy, like the sign of this is basically the hard-margin SVM. And then so the probability at least 1 minus delta, we have this bound on the 0-1 loss. So this is the key point here that you can see doesn't depend on D. So it used to be like root D over N. As root gamma, like rho over gamma. These are fixed, then this is a constant, and this part comes from the basically the bounded difference inequality. So this is the control over the expectation of the loss, basically, which is different. And so the key is that this bound does not depend on D because of the margin we achieve that. And then you actually show this for a larger loss. So we show that the ramp loss is actually bounded by this, and the ramp loss upper bounds the 0-1 loss. So we have a stronger result, in fact. So questions, comments? Okay, so let me again recall. We're going to have multiple different notations. Hopefully you keep track of this. The first thing that we do is that instead of looking at the sign, you can see that I've defined the classifier as just a linear function. So instead we change the loss. Instead of having the loss be like L of hx and y be the indicator of hx not equal to y, we define the loss to be, so this loss is over basically, so this is from plus minus 1 cross plus minus 1 to r. Right, so what we do is we actually redefine it now to be from, you can have like from R to R basically. R cross R to R. So what we do is that we change the definition of the classifier. Its real value, then hx times y would be just the indicator of y hx less than 0. And so you can see this is equivalent. So instead of looking at the sign, we look at this real valued, and then the sign of hx being different than y means we have an error. And so the indicator of this product being negative is just a 0-1 loss, right? And we're gonna like do more abuse of notation later, but this is good enough for now. And then we can relax the general losses. We can relax to more general losses rather than this indicator less than 0. You can now see that I can like do the phi here, and y times h is roughly the margin. So we have like a different measure of the margin. And now the population loss is basically the expectation of this over a generic sample. So L phi of h would be something like that. Okay. Sounds good. And just again, for the abuse that we're going to do later, usually I will have HW x is WX. And so instead of writing L phi of HW x and y, we first write it as like L phi of HWZ, where Z is x and y. And then we also write it as L phi of just W and Z. Okay, so these are all the notations that we're going to use, and I'm going to write it as just phi of y WX. Okay, Z here is just XW. xy. So basically we'll have L phi of, you'll see I write something like that. This would be phi of basically wyx. These are all the notations that we use. The function h is basically equivalent to this w. And then instead of having like h of x and y, we can think of the loss as like between a function and the entire observation, which is z. Not the observation, but like the x-y pair. And then we also have this. So we're going to move back and forth between these notations, hopefully. So like, if you want to be precise, you should have we call each of them a different thing because they're different functions. But so the general use of notation, by some of the use of notation, you're going to use the same symbol. Okay, so what does the, so you can see here, I'm doing this, yeah, I'm looking at this form, for example, this phi is applied to y times wx. And so the 0, 1 loss is the one which is 0 on the positive part and then 1 on the negative part. The ramp loss that we're going to look at is like matches the 0, 1 loss here, but then linearly interpolates between the two. So you can see the ramp loss is bounded and also 1 Lipschitz. Okay, 1 Lipschitz follows from the fact that if you take the derivative in absolute value that wants 1. Right? That's where it's differentiable, which is almost everywhere differentiable. And the hinge loss is the one that just is 0 here and then linearly goes up as you have more errors. So this is convex and Lipschitz. Okay, and then you can see both ramp and hinge are upper bounds on the L0. So in terms of the notation, basically, the 0, 1 loss is this indicator function. The ramp, the hinge can be written as the maximum of 0 and 1 minus t. Sometimes you can write it as just 1 minus t, the positive part. Okay, if it's positive, it's itself. If it's negative, it's 0. And this ramp loss is basically the hinge loss capped at 1. So the minimal 1, and then the hinge loss. Okay, very good. Okay, here's my like summary of the abuse of notation. So L of h and z is L of h, x, and y. And then, so this is the first abuse of notation. And then when h is wx, lw and z is just lw, hw, and z, which for the phi losses would look like this. Okay, just look at it a little bit to get used to, and then you move on. So it's fairly simple. It's just basically, you can think of it as the loss between w and this sort of thing, which is just the plus minus 1 version of x. So you just flip the x accordingly, and then basically you can think of this as putting all the x's on one side of the hyperplane and then measuring sort of this sort of a distance. Okay, so now we're going to prove, so we actually started proving this result last time. So what we have here is, again, this is the notation that I'm using here. This is the loss applied to this without the sign. So that's the first notation that we use. So by assumption, so if you recall, so w hat n is the solution of the following problem. So w hat n is basically argument over w, norm w such that yi wxi is bigger than or equal to 1 for all I. And you also know that the true distribution is the true distribution is, or has this gamma rho margin property. So there's W star in ST minus 1. So this is W star norm 2 is equal to 1, such that this margin condition and this bounded assumption hold. And then I'll look at the set of all linear functions. Like this, for which W is in 1 over gamma times the ball of radius 2. Right? So this is the set of all W such that norm W2 is less than or equal to 1. So the first thing is that by the definition of the hard-margin SVM, we have this inequality. So you recall how we had this inequality. So this is hard SVM. How do we get that inequality? Anyone remembers? Yeah. So if you divide basically both sides of this, so we have yi W star over gamma xi is bigger than or equal to 1 for all I. And so you can see, compare this with this one, you can see that W star over gamma is feasible solution, and W hat n is an optimal solution. So this is sort of form of a basic inequality if you, so basic inequality. She's just writing the like optimality condition. And so you had W hat n, and the norm 2 is less than 1 over gamma because of the assumption. And so by the definition of H, we have that H hat n is in W. Okay, so H hat n, if you recall, is just W hat n x. So it's a linear function for which the weight vector belongs to this ball. So we have that. So now we repeat the process sort of that we went through trying to prove bounds on excess risk. So here we have, so L and Ln are the population empirical losses based on the ramp loss. The first thing that we note is that the empirical loss of H hat n is 0. Okay, so this is the first observation. So anyone remembers again why this was? So basically, what should we do here? So Ln of H hat, or H, let's say HW is 1 over n summation I from 1 to n. This is phi, right, of yi wxi, where phi is the ramp phi. Okay, which is this guy, which is 0 here. Sorry, 1 here goes color here. So this is like 1. So this is 1 here, 1 here. And so this is phi ramp. So the thing is that if I apply this to basically, the claim is that Ln H W hat n is 0. So the hard SVM doesn't know about the margin because it's just solving this problem. Okay? You don't know the margin through margin. But how about if you look at the feasible region of this, right? So the solution here, so W hat n definitely sort of satisfies these, right? So W hat n xi is bigger than or equal to 1 for all I. Yeah, so t is like at least 1, so the phi is 0. So this thing is going to be 0 basically for all I. For all I. So basically the hard-margin SVM has empirical like RAM plus 0, right? And also the L01 loss is also 0 because that's an upper bound. Also the hinge loss is 0. So all of them are basically 0. But that's the empirical version. It's not. So this is like saying you have 0 training error, right? 0 training error. But this does not necessarily say that you have 0 test error like the generalization error. So what we can do is now compare this is the generalization error, right? Or test error. So this would be, I'm going to look at the difference. This one is 0 by the observation that we have. So when we look at the difference of the population empirical loss, the empirical loss is 0. Now this is bounded by the supremum or the class H, right? And if you just plug in what the definition of these are, that's this. And then, yeah, this goes back to my previous notation. So LH phi of Z is something like this. Like in my abusive notation, I'm writing this now again as L phi of H and Z, but that doesn't matter. So this is closer to the previous notation that we're using. So this is basically supremum with this difference. This is like an empirical process, right? So this is the supremum of a centered empirical process. And so we know how to control this. Basically, if you define this phi to be, sorry, F to be the L phi, yeah, I should write it like this. This would be like L phi O H, which is just equal to L phi H as H varies in H. Okay, that's our loss function class notation. Then this supremum basically is controlled by twice the expected Rademacher complexity. And there's no absolute value here, you can see. So you actually don't pay the absolute value if you go through the symmetrization argument. Basically, you just get the Rademacher complexity of this function class. And so then this is also the part where you pay the extra price. So this you have to go back to our arguments, but that's sort of up to constants if I'm correct about the constant. But the thing is that the expectation of, so the expectation of this, so expectation is less than or equal to this, and then the high probability bound follows from that. So this is, expectation is basically bound on expectation, and then so what is this loss function class basically? So if you ignore this n here, so FOZF is just basically L phi, you ignore this H. So L phi OH OZ basically. So if you just expand, what this turns out to be is just it's just phi. That's this whole thing is just this set of basically, this is just a set of all vectors that look like, remember L phi H Z1 up to L phi H Zn as h varies in h. But this is just, in our case, it's just phi yi, or y1. Let's say phi, yeah, phi y1 h x1 dot 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 phi yn h xn as h varies in h. So if you look at the Rademacher complexity, you have to multiply each one of these by an epsilon. And so that would be the Rademacher complexity. Then I have this inequality. What is this inequality here? Just remove the phi. Contraction, yeah. So this is contraction lemma. Phi, like phi ramp, is 1 Lipschitz. So actually the other one is also 1 Lipschitz, the hinge loss. So now I have this nice thing. And then what is this step? Is equivalent. Why? Yeah, so each one is just multiplied by some arbitrary sign. So here, like, we're conditioning on x and y, right? So the only randomness is here. It's just this is a new random sequence of Rademacher. So we got rid of that. And this is just the Rademacher complexity of this function class h ox. And this is what we did. So this is like a linear class, right? And this is bounded by, so we did it for W in the ball of radius 2. Sorry, radius 1. So let's go back up here. Yeah, so I'm assumed here the W is in unit ball, but you can see if because it's linear in W, if you rescale it by a factor, it just comes out. So if I'm doing it for like 1 over gamma here, I'm just going to pay a 1 over gamma here, right? So assume gamma is equal to 1 without loss of generality, and then the rest of the argument goes true. So this is basically, so yeah, so if you recall, this is, what's that? Yeah, so this is like that, or yeah, let's say R, basically H2OX is just rho over gamma root n. If you multiply by n, that's what we showed. And so that's what I'm going to use here. Where is it? Yeah, so you get root n gamma over n, and then there's a factor of n here that I sort of discarded. So when you divide by n, this will get basically R FOZ over n is bounded by rho gamma over root n, right? And then I take this right-hand side doesn't depend on the z's, right? So I get FOZ over n less than rho gamma over root n. So this is with respect to z basically. Okay, so we get that this is like twice gamma, rho gamma over root n, or if you go back up here, it's just this. Okay, and this part just follows from the fact again that this empirical process. So this part again is the expectation bound on this, and this is saying that this empirical process is close to its expectation. Okay. So once you put all these pieces together, you can see you can prove some sort of a fairly sophisticated result, but each piece sort of separately is quite simple. So this part comes from the bounded difference property. This part comes from controlling the expectation of the empirical process, but over a particular class for which we have a nice control of the Rademacher complexity. Okay, so given the tools, you can see the proof is not that long. Okay, sounds good. Questions, comments? So the main part was just to control the Rademacher complexity and just the combination of the result that we had for the linear class with bounded like input domain, and then the contraction, sometimes called Talleyrand's sort of contraction principle, for Rademacher averages. Questions? Okay, so this gives us a nice result. It's saying, what this is saying is that basically, if you solve the hard margin SVM, as the sample size grows, so your 0-1 loss, like the empirical 0-1 loss is 0, and the population of the generalization loss also goes down 1/√n, which is quite nice. So you recover. Yeah, this is like sort of the best thing that you can say here. To the best, whether it's best or not, whether you can remove this root, I'll leave it as is. It might be possible to remove this. So the best rate might be 1/n, but this is good enough for now. Let's move on. So one thing that we can discuss at this point is that now what happens if things are not separable, right? Which is a very natural state of affairs. So as we mentioned, if your function class, or like so basically you map to a higher dimensional space. So you have a feature map, you map your data into higher dimensional space. It's reasonable in the high dimensional space to assume things are separable. But you don't want to necessarily assume that in case things are not separable, you don't want to. So what happens if I try to solve this hard SVM and things are not separable? Something like this. Yeah, so the feasible region would be like empty. So this doesn't even like degrade gracefully. So you want something that at least like give you something, right? So what is a natural thing to do here? If you have seen the solution, so probably you know it, but see, I might have some sort of a point, like some of the red points might be right to this side. I could have like some things here, and some blue points might be like there, right? Then there's not going to be possible to like separate them by linear hyperplane. What can we do then? Distance to the margin, but also there's the sign issue, right? So the thing is that the distance to the hyperplane, so the margin would be the distance to the hyperplane. The distance, these might be fine, but they're on the opposite side. So some of them like have basically negative margin in a sense. So what you can do is, let's say if you call this the margin, right? If this is the margin, so you can find a hyperplane for which the majority of things are positive, but for some of them, this would be negative, right? What I can do is that I can let, so if you recall what we did is, what I can do is that it's equivalent to just allow some slack here. I just minus something which is positive and let this be big. So if this is big enough, then this allows me to, so we call this is like equivalent to being positive, right? So we divide it by something to get 1. So if I allow something like some slack here, negative like Ci, if Kci becomes large, this sort of, basically this condition is vacuous. You don't have to worry about it, right? So by basically doing this. So by basically requiring something like that, where Kci is bigger than 0, for some particular data point, I might allow Kci to like go to infinity, then this condition is like automatically satisfied. Right. So once QCI becomes very large, this can be any like, negative number. But then you don't want to let this happen for every point. You just want to let it for as few points as possible so that you get a good separation. So the idea is just to penalize by the total sum of these, right? Modulo sum of 8, so you put a lambda here. So without this QC, so if QCIs were 0, this is just minimizing this norm subject to this part. It will be hard SVM. Now I add these slacks and then add them to the penalty. I wait. So 1/n is for convenience. This lambda just controls the how much you want to penalize. So if lambda is very large, then this is close to the hard SVM. If lambda is very small, then you allow a lot of slack. Yeah, so if lambda is small, is it the other way around? Yeah, if lambda is very large, basically this part is not there. So you're, well, actually you allow a lot of slack. If this is small, then this is dominant. So you just, so when lambda goes to infinity, this would approach. So lambda go to infinity, soft SVM. This is called soft SVM. This approaches hard SVM. Right. Oh, sorry, lambda goes to 0. If it goes to 0, basically the penalizing the slack becomes very strict. If it goes to infinity, basically anything goes, right? So this is as if it's not there, you can do anything you want. So lambda to infinity is not good. Lambda to 0 is like the hardest here. So you can see there's this regularization parameter that allows me to like tune how like strict I want to the separation to happen. And then basically the rest is just minimizing the margin of the rest, sort of. So SVM penalizes data lying in the margin in addition to those that's classified. So there is this point which I'm going to skip. Is there any question? So this is again a convex problem because this is a convex function. And this is a convex set, right? Both are nice. So this is the feasible region is still linear, like fine inequalities, and then the cost function is like we just added a linear function to the cost function. It's almost as simple as the previous one, but this is now much nicer and much more practical. So this is the usual SVM that you would use, but we can sort of manipulate it a little bit. Again, for simplicity, I'm going to assume that this B is 0. So now I have these two conditions, right? And the claim is that I can write it as compactly like this. Why can I do that? So just writing these two conditions. So this and this is equivalent to that. Yeah, so QCI is bigger than 1 minus yi w transpose xi. And the other condition is xi greater than or equal to 0. These are equivalent to saying that QCI is bigger than the maximum of the two, right? And now what I have is like minimize over w and QC lambda plus 1 over summation I from 1 to n. QCI, and then I have QCI is bigger than or equal to max 0 and 1 minus yi w transpose xi for all I. So now what kind of simplification happens here? It's not like, don't look at the solution. So what happens, for example, if I first minimize over to C? Fix W and then minimize over to C. So I can eliminate basically minimization over QC if you think of it as that. What kind of equal? Can you say that? Like, okay, great. Yeah. So basically, the cost function is like separable in each QC. So separately, I can just minimize it. I'm basically minimizing QC1. So like QCi subject to this constraint is just a linear function, right, over like a half interval. So it has to like touch the boundary here, right? So the solution here, the optimal solution for QC is the minimum of the boundary, or like the boundary basically. So you get min over W lambda norm W squared plus 1 over summation. Yeah, let me not write it. So you just basically just plug into this. Right? So what we get here is this result. Right? So we eliminate QC, we're minimizing over W. Now W is like on constraint and constraint. And then if you recall this phi of hinge, which is this is basically phi hinge, say yi W transpose xi. Right? And using this notation that we introduced, right? This is basically L phi hinge of W and Zi. Right? Using this sort of abuse of notation, if you will. So this 4, or this previous one, these are equivalent. 3 or 4, this is the soft margin SVM, right? But you can see the soft margin SVM is like a very natural empirical loss minimizer. Right? So this is an ERM with L2 regularization of the weight vector. W, right? This is sometimes called like Tikhonov regularization, or like in like deep learning ML people, what do they call it? One knows. So they have their own terminology. Their weight decay. It's like it. Not in this context, but just regularizing by the L2 norm. It has many names. We'll see it's just for the regression. The regression, this is called the ridge penalty, right? So if this was the squared loss, it would be the ridge regression. But this is so it's an ARM with a regularization. So this is slightly different than the things that we used to look at. So used to look at, let's say, minimize. We restricted the class of functions, let's say W in W, 1 over N. These were constrained optimization problems, and W and Zi. So this is usually what we have been looking at. So you restrict your class of W. So for example, hard margin SVM would look like something like this. But now we just have a penalty here, which does the job. Instead of like, restricting the parameter to a set, we just gradually penalize it. It's similar roughly to just adding an L2 constraint, right? But it's much nicer in a sense because here you don't need to know a bound on W, like the norm of W. You just this is implicitly encoded in the, so you vary lambda. So you can choose lambda by cross-validation. But it's sort of equivalent to an L2 norm penalty. That's how you constrain. Questions? So what I want to do next is to prove a result about the soft SVM from that book by I forgot the name of the first author, but Ben David, the second author. So it's an interesting proof. I just want to give that. There are other techniques that you can do to analyze this. We'll use rather market complexities again back maybe when you do ridge regression. But I want to also do this because it's an interesting idea. So this is a different kind of proof. Any questions before we move on? So I just want to. So this is related to this notion of a stability, or like leave one out. Let's say cross-validation, something like that. So suppose I have. So the idea is that this regularization sort of improves the stability of the solution. So if I perturb, basically, just remove one of the samples, replace it with a new sample. If lambda is sufficiently large, the solution shouldn't change much. Okay, so the solution is like biased towards 0. Without lambda, there's no like way of controlling how wildly it varies. But if there's sufficiently enough regularization here, I can say that if I choose like exchange one sample for the other, the solution doesn't change. So it's like sort of a perturbation result. So suppose we have z1 up to zn plus 1. They're either from P. So h hat n be the ERM based on these. This is like the yeah, we'll see. Like for now, let's say they're constrained as usual. So h hat n is the ERM based on the LNH. LNH is the loss based on the first set of samples, so LNH. 1 over n summation I from 1 to n, L, H, and zi. And then what I'm going to do is that I replace the ith sample with this new sample and just throw out the ith sample. Now I have another set of n data points. I'm going to call like the loss based on this Ln plus 1i. The notation is not good, but I should probably do something else here, like j from 1 to n to avoid being clash of notation with the I. So let's say that's this, and this is also, let's write as j. All right, so I minimize this loss, the solution, I'm going to call h hat n plus 1i. Minimize this other loss, empirical loss, I get h hat n. So the only difference between them is that the loss function is changed at, oh, sorry, this is, it's like j from 1 to n, and j not equal to I. And then plus basically L, H C M plus 1 over n. It's just over that new data point instead of the ith data point. So I minimize each one and then I have these notations, hopefully clear, like they seem similar notation. And then I'm going to also do this notation for simplicity. The difference in the loss function between two functions at a given z. Okay, so you have a loss function, fix z, and then you apply it to two different functions. The difference I'm going to write is delta LH and H prime z. We'll get back to this. So the setup is clear. Okay, so the first thing is to state this sort of stability idea. So suppose I draw I uniformly from 1 to n. So the probability that this index takes any one of these I12, like values from 1 to n is 1 over n. Randomly pick one coordinate, basically. So I have this result, which is, if you want to unpack it, it's saying that this is the population loss minus the empirical loss of the ERM, the original ERM, right? So this is saying that if I look at this, the difference between basically the generalization and the training losses of the empirical ERM, if I take the expectation here, so the expectation here is over z1 up to zn, which is the randomness in the training using h hat n. Okay, randomness of h hat n is equal to the expectation of this difference in the losses between these two estimators that switch one data point. But then this data point that it switch is also random. So I randomly pick this. This is random. The randomness here is independent of everything else. So randomly pick one of the elements, like one of the data points, switch it with a new data point. That would be this estimator. And then the original estimator, the difference in loss at that random data point that you switch, right? Switch out, the expectation of this. So this expectation over all the randomness that there is. So it's like over the randomness or z1 up to zn and zn plus 1 and I, okay? So it is, this is like, this guy doesn't depend on zi, right? Zi is switched out, this depends on it. And this is saying at that particular data point, basically, this looks like a cross-validation error. So this is like, training has seen this, training has not seen this. And the difference in the loss at that data point between when you see it and you don't see it. And the averaged overall, like, it's like a very average sense thing, but it's saying that there's this connection between, that this side doesn't have anything to do with perturbation, right? So this is saying just on average, if you look at the difference between the training and the generalization loss of an ERM, that is related to this stability sort of in the ERM problem. So you switch one data point and that randomly, and then evaluate the function, the loss of the function that I fit on the new data points, the new training versus the original training on that data point. On average, this would be equal. So the proof is quite simple. So basically, we look at these two terms separately. So if I look at first this term, I look at the expectation of this. The first thing to note is this expectation is equal to that. So why is that equal to that? So Zn plus 1 is independent of Z1 up to Zn. So I'm basically evaluating h hat n and a new data point. I take the expectation. So if I take the expectation over Zn plus 1, that would be basically, so if you want, L h hat n would be expectation over Zn plus 1 of L h hat n and Zn plus 1. This is just a new data point, right? H hat n is like fixed now. Like the training Z1 up to Zn are fixed. If I take the expectation over this is just evaluating at a new like generic sample. And so this is the generalization loss, right, for H hat n. And then I take another expectation, right? Then I put another expectation here. Now over Z1 up to Zn. And like by Fubini, basically these are independent, so you're doing iterated expectation. So this expectation over everything, both. So over Z1 up to Zn and Zn plus 1. Clear? Right, so then I also have this, why the second thing holds. It's a similar reasoning. Yeah, exactly. So on average, basically they're saying, so this is like based on Z1 up to Zn plus 1 excluding Zi, and then Zi is a new data point I'm evaluating. So if I take the expectation first to Zi, it's just basically L of this guy, and then I take another expectation over. So this is basically by symmetry. So when we average things out, and this holds for any I, right? This holds for any I. Because it holds for any I, now this is like a function of I. If I plug in a random I, and it takes expectation over it, it's just going to be the same. So this saying this side is constant. This is saying that this function of I, this is like, you can think of this as some, I don't know, gamma I, if you want, or I don't know, what should we call it? AI, right? And then so AI is equal to expectation L h hat n for all I. So this means that if I put I here and take the expectation, that will be again the same as this. Right? It's just I'm plugging in I, take the expectation. Again, because of independence expectation is like iterated expectation. So first you take the expectation over these, and then over I, so you can combine everything. So this is there. Right now, if you look at, is it clear? So then the other point is the other thing. So now I want to control the expectation of Ln h hat n. If you expand this is just 1 over n, the summation. I move the expectation inside. Right, that's just by definition of Ln, and Ln is basically based on Z1 up to Zn, and then so then you have this equality here. So why is this? So, right, this is some, again, this is like some, like VI, okay? So you're saying like average over I from 1 to n of these. And so this is equal to the expectation of B evaluated with I, right? And this is over I. And then I combine the two expectations, right? Expectation over I. This is expectation over the randomness here with respect to yeah, so there's a little bit of a yeah, you just have to, this is expectation with respect to Z1 up to Zn, let's say. Z1 up to Zn. Right. So there's no randomness left here. And then what I have here is just the expectation over Z1 up to Zn and I. It's just argue it for yourself. It's rather simple. The trick is because you're averaging over everything, things sort of work out. Okay, sounds good. So then if you just compare, if I subtract these two, I'm effectively subtracting the expectation. I move out this minus this, and you can see by the definition, this is just a delta loss. So the loss of this minus the loss of this guy evaluated Zi. So that's the definition that I had there. Okay. Sounds good. Okay, it's an interesting result, but it's like you can see there's a lot of averaging going on. So on average case, this happens. Okay, so let's move on. Now I'm going to use this result. What basically we want to show is we want to control this difference in the loss. And the thing is that this quantity is nice for when you regularize. Because we perturb a little bit, because of regularization, you can imagine this doesn't change much. So consider, again, the setting that we had. Now HW is a linear function. Our loss is written again in WZ. And then I'm going to look at the ERM now. Okay. And to be honest, this, so this, so I should have sort of, so if you go to the proof, we didn't use the fact that this is minimizer over a particular edge or anything. It's just that the h hat n is based on, so the only thing that we used here in the proof of theorem 2 is that h hat n is based on z1 up to zn, right? And then h hat n plus 1 is based on z1 up to zn plus 1 zn, the ith location. So there's no, they can be used for if these are regularized or whatever, right? This doesn't use this, so I should remove this. So they're not necessarily solutions of this at this point. It could be the solutions of the regularized sort of losses, as long as they're just dependent on. So this theorem 2 holds for that case. So in particular, we're going to look at the regularized version, and then instead of h, we're going to look at the w's. So w hat is the minimizer of this empirical loss plus the regularizer. That's an example. For example, the soft SVM looks like this with the empirical hinge loss. So if I define this function to be f and w, the key observation is that if LNW is convex, which is the case for the hinge loss, not for example for the 0,1 loss, then this function, then f and w is 2 lambda strongly convex with respect to the L2 norm, let's say. Usually when the norm is not specified with respect to the L2 norm. So let me ask you, do you know about strongly convex functions? So what is a strongly convex? Okay, you can add a quadratic lower bound. Yeah, so one way to see it is that the functions have a quadratic lower bound rather than just, for a convex function, you just have like a fine lower bound. But for these strongly convex functions, you have a quadratic lower bound. There's a like a formal definition which is given here. I'm using sort of the notation from these convex analysis books. So there's this sort of Euclidean type. It's not Euclidean, but it's like an, this E is not the expectation. It's just let's say a linear space, vector space. And then if you have a function from negative infinity to infinity, including infinity, it could be like just extended valued function. It's sigma squared strongly convex over the domain of f. Domain of f is very dome f set of all x's such that f of x is less than infinity, right? Finite. If the domain is convex and over the domain, basically you have this inequality. So if you look at this alpha in 0, 1, so this part is convexity, right? And then you relax it a little bit. So this goes away. So this is saying, it's actually not relax it, just strengthen it. Because this is saying, this definitely is upper bounded by the first half. So this is convex, but it's saying that it's even bounded by something smaller. So if E is a Euclidean space, which means that this norm, so this could be any norm. This is slightly more general than this definition, but this is the more intuitive definition. So if E is a Euclidean space, which means that the norm comes from an inner product, like the L2 norm, then this definition is equivalent to saying that F is strongly convex, sigma squared is strongly convex if F minus sigma squared over N times the norm. So this, if I subtract this much of the norm from F, then this is going to be convex. Okay. So if E is not Euclidean, they're not equivalent. But okay, I see that we're out of time. So next time I'm going to come back and to continue. But with this definition, it's clear if I add something like lambda over this, and if this is convex, now if I subtract, let's say 2 lambda over 2 norm squared from this, it's still convex. This has to be like 2 lambda strongly convex. Okay, we'll come back next time and continue. Thank you, guys. Bye. Thank you. See you.